In this lecture, I'll discuss first order low pass filters and high pass filters. As we all know, a filter is a frequency selective network which allows a certain band of frequencies and rejects all other band of frequencies. Now let me talk of first order low pass filter, a frequency selective network which allows only low frequencies and attenuates high frequencies. And this low pass filter is going to allow frequencies up to higher cutoff frequency. And talking of first order, if you are going to derive the transfer function, the order of the denominator is said to be 1, and that's why we are going to call it as a first order. And at the same time, talking of physical realization of first order filters, we are going to have only a single RC section, and that's why we are calling this as a first order of filters. And one more point with respect to first order filters is the roll-off rate with respect to a stop band is said to be 20 decibels per decade only. And these are all the features that are going to add to the first order of filters. And this is the circuit diagram representation of first order low pass filter. And here the input is applied to non-inverting terminal. Normally we prefer to use non-inverting amplifier configuration of the operational amplifier. Why? Because non-inverting amplifier has high input impedance and low output impedance. Therefore signal won't be loaded. In case of filter circuits, we are interested in passing the signal as such to the output. That is also within the limited frequency range. That's why the signal should not be loaded. In order to avoid loading effect, we can have high input impedance and low output impedance. And that's why we prefer to use non-inverting amplifier configuration of the operational amplifier. This circuit seems to be simple. Why? Because we have RF and R1, and initially we are going to form low pass circuit, and the output of low pass circuit will be applied as the input to the operational amplifier. And therefore this RC section will behave as a low pass filter, and we are going to prove the same. As this is connected in non-inverting configuration, V0 can be simply written as 1 plus RF by R1 into V1. If first we will derive for V1, and if for simplicity's sake, let me consider Laplace transforms. Therefore the Laplace transform for this C, we can write it as 1 by SC. Therefore V1 will be written as a Vin into potential divider arrangement 1 by SC divided by R plus 1 by SC. If you are going to simplify, V1 will be simply 1 by 1 plus SCR into Vin, and substituting S equal to J omega is the expression, and omega equal to 2 pi f, and substituting this V in this V0 expression. V0 is equal to 1 plus RF by R1 into V1, and here we have a complete brace, and this is into. If V0 equal to 1 plus RF by R1 into 1 by 1 plus J 2 pi f CR. And to talk of the gain, V0 by Vin, we can write it as 1 plus RF by R1 into 1 by 1 plus J 2 pi f CR. And from this we can't justify whether it is a low pass filter or not. Therefore let me consider the magnitude expression, and before moving on to that one, for simplicity's sake, let me consider the higher cutoff frequency fH to be equal to 1 by 2 pi RC. Therefore V0 by Vin is equal to AF by 1 plus J 2 pi f RC, and AF is nothing but 1 plus RF by R1, and we have already considered fH equal to 1 by 2 pi RC. Therefore we can write it as AF by 1 plus JF by fH. V0 by Vin is said to be the gain of the filter, and AF is the passband gain of the filter, F is the frequency of the applied input signal, and FH is the higher cutoff frequency of the filter. The magnitude of the gain, that is mod of V0 by Vn, and here we have some complex term, therefore we can simply write it as real term can be directly taken as AF divided by, in the denominator, for complex functions we are going to write that as a root of uh, sum of squares of coefficients of all the terms within the expression. Therefore it's going to be root of 1 plus f by fh whole square, and the phase angle can be simply written as phi equal to minus tan inverse of f by fh. If it's going to be in the numerator, you can simply write it as tan inverse of f by fh. As it is said to be in the denominator, you are going to write it as minus tan inverse of f by fh. And consider there won't be any phase change for the real terms. Therefore numerator we are not going to have any phase change. Now, talking of the frequency response of the low pass filter, this is the gain expression. Therefore try to substitute different frequency values. First let me substitute f equal to 0. If f is 0, this whole term is going to become 0. Therefore the magnitude of the gain is AF. And try to consider f equal to fh. For the magnitude of the gain is AF by root 2, and for f much greater than fh, it is going to be greater than root 2. Therefore the gain is going to be AF by greater than root 2. Therefore the gain is going to decrease from AF value. And for f equal to infinite, the gain is going to be equal to 0. Therefore if you are going to observe from this expression, initially there is said to be a constant gain up to a value of cutoff frequency, and after which the gain is going to decrease and it may reach up to 0 at infinite frequencies. And that's why the circuit behaves as low pass filter. And you can observe from the transfer function we have got a first order expression only. Therefore the decay rate is said to be minus 20 decibels per decade. That means for a 10-fold increase in frequency, the gain is going to fall by 20 decibels. And as the gain is reducing, we are going to notate that with a negative sign. Now let me talk of the filter design, how you are going to design a first order low pass filter. And while going for the design, nothing but we are supposed to calculate the component values by having some specifications. Normally the specifications with respect to filter design is up to which frequency we are going to allow a signal and what should be the gain within the pass band. Therefore these are the two specifications we are going to have. Therefore choose the value of higher cutoff frequency. This is one specification. Next one, how about the pass band gain? Therefore fh is given by 1 by 2 pi rc. Therefore we have one expression and two unknowns r and c. It is not possible to calculate both. Therefore we'll be assuming one value and we'll be calculating another value. Therefore you are going to assume capacitance value and it has to be less than 1 microfarad. Then calculate the value of r using r equal to 1 by 2 pi fh into c. And that's how we can get r and c values. And select the values of r1 and rf dependent on the desired pass band gain. And the pass band gain is 1 plus rf by r1. And that's all about low pass filter design. Let me consider a simple substitution problem. Design a low pass filter for a cutoff frequency of 1 kHz and for a cutoff frequency of 2. Therefore we are given with fh equal to, and this is gain, it's a typo, for a gain of 2. Therefore we are given with fh of 1 kHz and AF is equal to 2. Therefore assume C less than 1 microfarad. Here I have considered C equal to 0.01 microfarad. Therefore calculate R by the formula 1 by 2 pi fh into C, that is substituting, you are going to get one value. And from the pass band gain, which is given as 2, is equal to 1 plus Rf by R1. Therefore Rf by R1 will be equal to 1. Therefore Rf will be equal to R1. Therefore choose R1 value. Therefore Rf will be again equal to the same value of R1. And that's how we are going to design a low pass filter, and that is also specifically first order low pass filter. Now next let me talk of a first order high pass filter. For the same reasons we are going to call this as a first order high pass filter. Now let me talk of high pass filter. It's going to allow higher frequencies and attenuates lower frequencies. Therefore it's going to allow from a frequency, and that frequency is going to be called as lower cutoff frequency. And why we are calling this as lower cutoff frequency means this is the minimum frequency which can pass through a high pass filter. And the circuit representation is going to be the same unless for the altered positions for R and C. If here V1 is a Vin into R by R plus 1 by SC. If you are going to simplify, V1 is Vin into SCR by 1 plus SCR. Therefore V0 is equal to 1 plus Rf by R1 into V1. Therefore substituting a V1 in this expression, it's going to be V0 equal to 1 plus Rf by R1 into Vin into SCR by 1 plus SCR. We can write this 1 plus Rf by R1 as AF, and substituting j omega at the place of S, and at the place of omega substituting 2 pi f, and considering cutoff frequency FL equal to 1 by 2 by RC. Therefore the gain of expression is AF into JF by FL divided by 1 plus JF by FL. And from this we can write magnitude of the voltage gain AF into, here we have complex term, therefore you can write it as root of F by FL whole square divided by, here also complex term, root of 1 plus F by FL whole square. And this root and 2 gets cancelled, therefore we will be left with AF into F by FL by root of F by FL whole square plus 1. Substituting different frequencies, for f equal to 0 it's going to be 0, and for f equal to FL this is going to become 1 and this is going to become 1, it's going to be AF by root 2, and for f greater than FL the gain is going to increase and it's going to become constant. Therefore initially 0 slowly raises and reaches 1 by root 2 value at cutoff frequency, and finally it's going to become constant. And that's how this circuit behaves as high pass filter. And the design of the first order high pass filter will be similar to the design of first order low pass filter, but the only difference is instead of FH will be given with FL, and the design procedure is same as a first order low pass filter design. That's all.